Record on this computer. Good. Okay. So everyone, we're going to record, and I guess we're going to have, it's 5:03. It is a holiday in the United States, so I wouldn't have expected that many people. I thought I would have a nice little background just to make you feel at home, I think, especially if you're coming off campus. And as you'll see on the desktop, we have our folder here, problem set 5 at the end with the R code. Now, since there are a few of you, I invite you, I urge you, in fact, this is your education. So if you have any questions that are specific, feel free to interrupt, feel free to text or chat. Otherwise, I'm just going to go ahead and basically give you a rundown on simple linear regression. And this is actually one of my favorite weeks. Actually, regret not attending last week. But simple linear regression is pretty cool because what you guys are learning today is essentially the basis of modern statistics. And that's a really, really cool thing to be able to do. Already, you're using R programming. You're basically a programmer now, whether you like it or not. And you're learning linear regression, which is the foundation. It's often called the workhorse model of statistics. When I say it's the foundation of statistics, in a way, it's because it's a lot of other types of ways of analyzing data are simply variants of the simple linear model. I'm going to actually show you this one little bit of help. I'm going to open up and share my screen. I'm going to open up my window here. And I want to show something to you. We have this little website right here. I'm going to put this in the chat. When I provided you guys with a tutorial on help, I failed to mention this nice little website. It's called Cran Task Views. And I think it's appropriate to start off with this because it looks pretty bewildering. But it's another way to get help if you're looking for a particular type of statistical analysis. So keep in mind, each week we're taking on a different hat. We're taking on a different role. Well, look at this. If you're interested in chemical analysis or computational physics, there you are. If you're interested in the economy, here's econometrics. Finance, there we are. But I just want to point this little thing to you, this little segment right here. Multivariate statistics. Well, that's what the linear regression model is. And that's what's so exciting this week, is that basically we are starting our odyssey into the world of multivariate statistics. And this is something we could talk about later. And if you see the lattice function, I just want to show this to you. Actually, I'll put this in the chat history as well. You can save that. These aren't things that you have to learn. I'm just pointing this, giving you, I guess, a taste of what to see, and to recognize that what you're seeing and learning today, like the scatter plot function, the lattice functions, let's see where the LM function. Well, I don't know if we see it here, but regardless, everything you see here, basically we're beginning. Oh, here we are from stats LM. So here we have the linear model. That's what I was looking for. So that's why I'm so excited to introduce this, because this is like the first step of a really cool trip. And it's one that will take you forever and ever. I still do linear models. I did a linear model today, actually. So it won't leave you. There are some interesting debates within statistics, and we can talk about that later. But let's now dig deep into the generalized linear reality. So what are we doing this week? We're going to look at this interesting data set. So alas, we're going to have to cover up this nice little view of Harvard Square. What I did is I actually went to the problem set page, and I'm going to actually make these into a list, and I'm going to increase the size of the text here. Oh, okay. We'll take these, turn these back into icons. I want to point out that I had downloaded some of the images that were part of the problem set. But as is usually the case, we're going to emphasize, we're going to focus on the syntax and the R data file. And then when you work in RStudio, you'll see this little thing pop up. Well, what is that? That's when you start an R session, it'll remember where you are. And so RStudio is kind of like a good friend who tells you where your car keys are. You know, where are your keys? Well, when you open up in a location and then you reopen RStudio, in fact, I did this when I started today, it had a file that was open that I hadn't used in like 2 days. Why did it do that? Well, because RStudio's default is to begin where you just left off. And you can just close that file. But again, I emphasize this idea of what is often referred to as a workflow. It's not very common in a lot of fields of social science, but it's really important to basically keep all of your analyses, all of your work in one little sandbox. I call it a sandbox. Basically, the point is you set your working directory. And I know we haven't talked a lot about that. A lot of this has to do with computer programming. But I just want to emphasize that here, I want you to get used to this idea that we have a folder that we've defined. We have a script, and we have a data set, or we're going to call these data frames. We're going to try to use R jargon right now. And I actually was playing around with this before we started this section because, I don't know, I like playing in R. So I wanted to show this to you because as you'll see, it's the same script as before. So if you don't have Mosaic installed, you have to install this. So I'm going to just rerun this. I'm going to use some keyboard shortcuts, by the way. You do Control-L, and you clear that console. You can also type, I believe. Let me make sure this is correct. I'm just going to define an object here. And then we print X, and then I want to clear the console. I believe you do CLS, but I'm not sure. No. Okay, some of this is muscle memory. I'm not exactly sure. But you can do Control-L, and you can clear your console. It doesn't mean you lose your history. In fact, you'll see my history. I was messing around doing some other stuff. But the point is, if you like to have your nice consoles cleared, I kind of like to do that. I'm going to teach you another word today. This is called evaluating some script. When I highlight a bit of script and then I run it, the word we often refer to is evaluate. I've heard execute before, but I don't think that's correct. I've heard evaluate much more often. So here we have the Mosaic Library. I want us to get used to these functions, and I'm not sure if they're totally familiar with you, for you, but we're going to, first of all, figure out where we are. So here we comment this out. Anything after a hashtag or a pound sign is a comment. So you can put it after the function, or you can put it before. But this tells us where on our computer we are working. And we often want to know this. We really want to be sure. It's sort of like your GPS. You don't want to just, I've seen some students come in and they don't really know where they're working, and then they change their working directory, and you really want to just define where you work. So before you do that, you want to really know where it is. Well, you'll see my path file. It's typically in quotes. When you work in the computer world, typically it's better not to have spaces, I would say. When you define, this is called a path file. So you can have a full path file. So this all goes all the way from, I have a Windows 7, it goes from C, users, Jodox 1980, which is a childhood character of mine. And then we have our problem set. And this is defined by our desktop. If you're on a Mac, you typically you'll have these little slashes as well. That typically needs to be in quotes. This whole thing is interesting because we can actually define this. This is one item. This is it's a vector of one. But I'm going to just copy and paste this. And this is what I want you to do. After you type that get working directory, then I want you to do this. You're going to set working directory to wherever it is you want to be. So if you want to be, say, a few files up, you can do that too. And you can be more complex. You can do this nesting function, which is something I've done before. I was playing around with defining items in your desktop, but I'm going to remove that. And if you want to remove an object, you just type rm parenthesis, and there we are. And I'm going to get rid of that little x that we have there. And I'm going to remove the data frame too. And I'm going to go actually, I'm going to erase this. And I'm going to remember that little broom, that's cleaning your environment. And I always encouraged you to clean up after yourself. And you know, when I was a Boy Scout, I was always taught, you know, you should clean up after yourself. You know, don't make a mess. You know, leave your campsite cleaner than you found it always, I think is what they drilled into our brains. And basically, that's what you want. You want to start off with an empty environment. So I know I'm, you know, emphasizing this quite a bit, but I think it's important to set your working directory. So this defines or sets your working directory. When you start out, I would define it by its full path. And the full path is just simply everything that goes all the way to the end of your computer. It defines the full length of where you are. Now, it's sort of like a relative path might just be, okay, now that I'm at my desktop, I want to go to this problem set, and I want to go to problem set 4, I want to go to problem set 5, blah, blah, blah. But let's just keep it simple. And I want to do this because then I want us to get used to using the script to load data. Of course, we can always do the drop-down menu, as I've shown, but let's load our data. But before we do that, I want us to see what's in our working directory. Well, this is pretty easy to do. In fact, you just do the dir function. If you know Unix at all, some of these commands actually, a lot of them are obsolete, but a lot of statistical languages come out of the Unix programming environment. So if you're a big Mac user, you like the terminal, look at this. Okay, we got a bunch of items here. We have 7 of them, actually. Now, as I told you, right, we have this desktop ini. Okay, that doesn't matter. We have PNG files. Well, we know those are pictures. Okay. What really are we interested in? Well, we're interested in 2 kinds of files. We're interested in scripts. So here we have the R scripts that we have open. And we want to load our data. I'm going to actually close that view. We should not view that. So let's just, now that we have that, let's just make this easy. We're going to do load. And then, oh, look at this. Isn't this nice? Well, why don't we do load? We'll just define it as violence. I'm gonna gamble with this and see if it'll load. No, okay. I didn't think it would. I just want to. Sometimes I like to play around, just to test the boundaries of what is possible. Typically, you have to be precise when you're programming. You have one little error. This is one frustrating thing when you program. One little thing that's off. You know, you have to start all over. So keep in mind that, again, R is case sensitive. So I couldn't get away with specifying violence, and that's good because we have to be precise. So all you have to do is do this. And look, we loaded our data frame. How do we know? Well, we evaluated, see, I use that term, we evaluated the function. We don't have any red here. There's no warnings. There's no error. And here we see the data frame here in our global environments, our working directory. And so that's very easy. Just load and make sure it's in quotes and make sure that the D of that data, that suffix right there, that's a capital R, capital D. Okay. I was doing some other stuff. We can talk about that later, but I think it's more for office hours. There's more advanced stuff. Okay. We've looked at this stuff before. But before we do that, I'm going to look at this. I think let's play around with this little data frame a little bit. Let's go to this view function a little bit. We're going to do violence. Gosh, it's kind of a violence data frame that we have. Looks pretty long. In fact, we know this because we can actually just look in our RStudio environment. We have 8 observations and 19 variables. This is an interesting data frame. It's called a high-dimensional data frame. So when we often talk about big data, most often people are thinking about a large sample size, like 1 million people, 1 million Facebook users. High dimensional data can also be very large. You can have 8 observations with 1 million variables. And that's going to be a big challenge for you to analyze. Anytime you have more variables or more columns than rows, it's defined as high dimensional. So you can just take a quick gander here. Doing this. I like to get back to the syntax. So I want to comment this out. I'm going to do, I just did Control-Shift-C. It's funny because sometimes you get so used to just the keyboard shortcuts, you have to sort of remember what you do. If you want to comment something out quickly, and this is good if you want to comment out a bunch of lines, you can hide all of this and just do Control-Shift-C, and it'll comment out. And I think if you do it again, it'll undo it. Yeah. So comment. So Control-Shift-C, Control-Shift-C. Okay. You can do the view. I kind of like to do the dimensions thing. This sort of gives you the idea of the row. You know, here we have the rows and the columns, rows and columns, rows and columns. In fact, this is how you do these. You know, break it out. Let's look at these names of this data frame, because we know this is a data frame, so we're going to look at the names here. And one of the things, like if you look at the question here, you'll see there's a question about murder rates. Let's see if that function actually works. I'm not sure if that's correct. Yeah, no. It's not. We're not able to define the objects here for murder, huh? I wonder why it's doing that. Well, I see someone had said, well, some of these functions don't make sense. That doesn't matter. What I want us to get started with is these are just descriptive statistics. We could do one method we could use, I think, is summarize. Look at the British. Summarize, and then what was the function here? Hold on for a second. Sorry. It's funny because I'm actually more used to using data frames that are outside of the Mosaic plot function. So I think one like difficulty a lot of people have with R is the fact that there's so many ways to do things. I just want to make sure that I have it right. Well, I would do, yeah, okay, we could do this. Stat.describe. Oh no, that requires a different package. That's fine. I'm not gonna delve into that. What I want us to get to is this scatter plot. Now you should have, I think, looked at scatter plots before. This should not be an alien thing to you. Let's get this going. Well, this is an issue that I've always encountered with RStudio, something I don't always like about it, which is that plot looks pretty squished, right? I highlighted that and I evaluated the syntax. We don't have to worry about the type here. That's sort of an argument. What I want to emphasize here is the modularity. That's another bit of programming jargon. The modularity of the syntax. Here we are defining an outcome as a function of virality. And then we define the data. And unlike some people, I like to put spaces between the equal sign. I think it's easier to read. I think that's sort of comme il faut, as the French would say. It's how you do things. But what we have here is we have a plot. But I'm going to actually delete that plot because that doesn't look very good. Yeah, we're going to remove that. So in RStudio, just keep in mind the dimensions of your plots. Here, I've been trying to sabotage plot creation because I've encountered this quite often. Let's see if we can do this. Maybe Mosaic Plot is Mosaic is too good for us. Yes, it'll always make a plot. Well, often when you use the base functions, what are often called just the standard functions within R, it will not create a plot. If you just use the standard plot function, it will complain. It won't even create it. You'll have a little red error sign. It looks like this guy, this is pretty robust. But let's just try it one more time. Okay, so this is a nice thing about this. Okay, about the Mosaic package, because it's actually pretty, we should actually say lattice. What I want to emphasize here is, here we have a scatter plot. So keep in mind, just remember, think of the y-axis here as the outcome and the x-axis as the predictor, because that's how you're writing it out as an equation. I know it's called an XY plot, but that's kind of, it's because we often think about the predictors of an outcome, I would say. I'm not going to delve into the minds of the developers here. But whenever I think about variables and I think about regression models, I think about what's on the right-hand side of the equation and the left-hand side. The left-hand side here is murder rate. That's the Y. The right-hand side is the X. And so this is, I'm trying to express this because this is the language that's, we're getting really close to thinking about the linear model. So now let's do a simple linear regression. And here we have what I would say, again, is the workhorse of R. We have this assignment operator, this little thing. I love this thing because you can basically define anything as an object. And this is, again, this is why R is called an object-oriented environment. OOE. Why is it environments? Think of an environment as like your sandbox, wherever you do stuff. It's not that complex. It's not more than simply a space where you work. Just think about environment. Object-oriented means, all it means is you can basically make anything an object. So if you saw me mess around earlier, for example, I define an object with the assignment operator as the value of 1. So here I define x equal to 1. Look at that. And here we have a value. Let's do b. We're going to assign to 99. Okay. Well, then let's do, let's print x plus b. Whoa, look at that. So here I am, and in fact, we can even do this. We can actually assign C100. Typically, we'll put spaces between these. So this is a hyphen. This is a caret. It's just right above the alt sign. We'll define this as a letter. Why not? There we go. And then if you want to print something, print, all it means is display in the console. You can just type it out if it's just text. Look at that. Or if you want to be more formal about this is like the tuxedo version of the print. You can do print, but it'll be the same thing. You print C. So this is pretty cool. So when you think about some of these problems that we have when we're doing some simple algebra or simple statistics, one of the cool things we can do is actually we can use the R environments. And one of my goals in this class is to actually post as a tutorial some, I wouldn't say hacks, but some ways to just answer some of these problem sets using the R environment. I use it all the time. If I want to, I don't know, figure out a percentage of something, or if I want to calculate the relative risk, I will do it within the console and within the environment. I'm going to delete this, however. But the main point is that here it's called an object-oriented environment because here we define things and we can mess around with them. So let's just remove these things. We'll remove the, I think, let's see if we can remove all of them. Let's see if we can remove more than one. Yep, so we remove 2 of them. So you can remove 2. Notice I put them in parentheses. Oh, here's another little tip. I think it's one of these things it's intuitive if you're a common user. The up and the down arrows. If you want to go back to where you came before and you don't want to go toggle this history bar, So if you want to like revisit the past, I can click here actually. No, I can't. Okay. See, I thought I could because I never actually use a lot of this graphical user interface. I will go up here. But this is really useful. So if you want to go back, you're like, oh gosh, I want to do this. I want to define this object again. I typically want to see the environment. I think that's intuitive. I think it's also something I like to keep clean if you're persnickety. So let's remove our X now. It's always better to put it within parentheses. You don't have to though. Okay, so now we have our data frame. Why did I emphasize this object so much? Because we're going to define an object, and it's called model. Now, this is an interesting word. A lot of people might be confused about this. I was talking with a notable psychologist, and this person thought of a model in a different way. But when we talk about statistics, think of the linear model as an approximation of reality. And in fact, there are actually there's kind of an interesting conceptual cultural war, you could say, within statistics. There are people, the history of statistics is founded upon the idea of a model, which is, in essence, here we have, just take a look at what we have on the screen. I'm going to try to make this bigger. These are the actual data, right? So here's rurality, whatever percent rural, and here's the murder rate. Well, it looks like the more rural you are, the higher the murder rate is. Well, we're going to model this. And what does that mean? Well, in some ways, we're going to make it up. We're going to impose something here. And the model itself is an approximation of reality. There's a famous saying by a statistician named George Box, all models are wrong, some models are useful. That he's being somewhat facetious there. But what he's emphasizing is the fact that we're not looking at every single data point, although that's always important to do. I always encourage you to look at your data. But when we talk about statistics, we're actually doing an approximation of reality. We're trying to summarize and condense it into a few variables, into an equation. So this model now, look at this, we have a list of 12. So it says, what is the proportion of variation in murder rate that is accounted for by the variable rural? Well, you can do just the R-squared of model. Look at that. The R-squared, that's the proportion of variance. And that is always equal to 1. Now, I'm going to use this popular round function. If you recall, we're always asking you to round items to 2 digits or significant digits, whatever. So keep in mind, here's if you're going to round object X, you do this, and you're going to do it to 2 decimal places. So let's define this as R squared. Sorry, I don't want to do that. So I'm going to define this object. I'm making it a little more complex, but I'm going to define the object. You're going to see this. Oh, look at that. Well, do we really need this many decimal places? No, we don't. So we want to round this R squared. So now we're going to do round dot R squared. We could say call that, and that is simply, we're going to define it as the rounding of what we just defined as R squared. And then we're going to do comma, and we're going to do it to 2 decimal places. And look, oh, it's suggesting maybe we could do 0. Well, where is it? Oh, that's right. We want to print this rounded R squared. So let's be formal about this. We're going to print our rounded one. Of course, I'm kind of cheating here. You can look in your environment. You should see it too. You have 61. And I emphasize this rounding function because I've noticed quite a few students in their problem sets are so close, but they're rounding off just a little bit. It's a very human thing to do. It's actually, scientists have actually looked at other scientists do rounding, and there's often an implicit bias. There's a bias toward rounding numbers in your favor. There's a bias toward rounding toward standard levels of significance. But I just want to show to you that we can define an object for an R squared, and then we can round it, and we have that rounding function. I know this is beyond what we have in the problem set, but this will help you for the problem sets. I just don't want you guys to get caught up on these little things. Okay, now it's asking us, write out the equation for simple linear regression model predicting murder rate using the input variable rural. Calculate or compute the predicted values for each of the observations in the data set, Okay, so this is the cool thing about the model, about objects. we could actually redefine this, even though we don't need to. We could define this as this like model 2. Or, and I'll remove it. Sorry. I'm going to remove model 2. The point I want to make here is that when you define a new object in your environment, just be aware of this, that the object will be, you'll override the other object. So here we're doing the same linear model, and then we're going to do this predict command, and we're getting the predicted values. Well, look at that. What happened here? Well, we took the values of rural, and we superimposed a linear model here, and we estimated those values. And this is what I'm talking about when this is one really cool thing about R, I think, is the fact that now we can do a lot of cool things with predicted values, for instance. We can define that as an object, for instance, and we can graph those. So if we print violence, we actually even get more information. But the point here is that when we use predict, we're actually using, we're going, think of the word model as an estimate. It isn't reality, it's an approximation of reality. It's something that is superimposed. It's in the same way when we started off talking about averages, there is no average person, technically. I mean, there could be, but the concept of average is actually relatively recent. It started with with industrialization, with what the philosopher Ian Hacking called the avalanche of numbers. We had so many numbers from the industrialization because people had to keep track of their records, and we had machines that finally automate a lot of information that we had to figure out what to do with this information. So there's an argument out there that the data preceded the analysis, actually. Other useful R code, yeah, so this is stuff I've spoken about before. How to load, how to view. Yeah, I think this isn't that interesting, but I do want to emphasize, and I've been kind of, I haven't been that forthright in showing you exactly what I'm producing here. But keep in mind when I talk about this print function, when I define a model, we can look at the regression coefficients here. We have the coefficients. So this is what's really cool about R, and I like it more than other types of statistical languages. Again, I'm referring to this equation, the language and the idea of an equation. But here we have the intercept, which is, what is the intercept? Well, it's the value of y when x is 0. And then we have the slope for rural. So a simple linear regression is I think, relatively simple. I don't know if there's much more to say about that except, okay, yeah, why don't we run this model? We'll just look at life expectancy. Yeah, that might be a little more interesting. And then you can calculate the R-squared again. But I want to show you this because I've been showing you the data, but we also kind of want to see our model too. And this is what we do here with the XY plot. So let's define our model again. Oh, look at this. This is really cool. This is what we're talking about now. So what's going on here? Well, we have the regression line here as well as a scatter plot, and they're superimposed. And this is another great thing about R, is the graphics are beautiful here. One limitation with R, I'd say, is that you don't have variable labels that are that easy to access. You can do some things with it, but typically variable labels are simply the names. That's quite often is what happens. But here we have life expectancy predicting murder rate. So murder rate, again, is the y-axis. Life expectancy, the predictor, or the number of years in that country that you're expected to live. Well, what do we see here? Is this a positive or a negative association? In other words, what does this say? Well, it says that given a country's life expectancy, we can predict your murder rate is going to be a little bit lower. And the reason we often talk about predictors, imagine if we go back to the rows here, notice how many countries we have. We don't have that many. Let's say we had, do we have Canada here? No, we don't. Let's say we had Canada here. Where would we think Canada would be based on our model? What would we predict if we had new data? Well, based on the data that we've collected, and of course we could always debate about the quality of the data here, because you can see this country rather is an outlier. This probably isn't a very good fit here. Nevertheless, in general, you could say, okay, here we are modeling the data. We could predict with some accuracy if we have new cases or new countries in our data set, probably life expectancy predicts lower murder rate. If you know the country's life expectancy, you can give the predicted value. So let's get that predicted value out. So how did we do that before? We did just predict model. So I want to copy and paste that because that's probably the easiest way to do this. And that's pretty cool because now you can see which country has which value, which predicted value. So in terms of murder rates. So again, when we talk about prediction, I want to emphasize, maybe this isn't clear. We're always predicting the outcome, right? X is predicting Y, X is predicting Y. So it's also called Y hat. It's a population parameter. So we could say, well, the murder rates, in South Africa is quite high. Which country do we think is the outlier here? Looks like it very well could. Which country has a murder rate that's? Let's look at our data actually. Which country has a murder rate that's high? That is that high. That is Jamaica. Yeah. Okay. So I think I'm right about yeah. So here we have a relatively high murder rate, the highest in the sample. So this would be considered an outlier. And sometimes we want to check, when we do regression, what is called regression diagnostics, we want to see what happens when you remove an outlier. And there's a big debate. There's no real answer about whether to remove outliers because they're information. My mantra is typically you don't want to throw away information. You want to keep your information. That being said, sometimes people will say, well, it doesn't belong here. It's entirely different. So this is where, again, going back to this idea of the workhorse of statistics, this is where theory comes in. This is where knowledge comes in to model building. And this is very different than a lot of new kinds of statistics that is called machine learning or algorithm-based learning. So that the new statistics are based on algorithms. You can say the old statistics, but the standard statistics are based on models. And models are typically based on a theory. You have an assumption, you have a theory of the world. And that's why, what you define as the predictor and the outcome is based on theory. It isn't based on, say, just the data, although some people often just heavily, rely heavily on the data. All right. So how do we get?
I had a question.
Now, what is the R-squared exactly? Did we, talk about this? Well, R-squared we can think of as the amount of the proportion of the variance in Y that is explained by X. So technically, the higher the R-squared, the better your model is. That being said, in practical analysis, no one really cares about R-squared. And I'm sorry if that offends people. I'm sure I shouldn't be saying this, but I've seen a very low R-squared before. So here we have an R-squared that's about 0.25. And that makes sense because if we look at what is not being explained very well by the model, we can see these countries right here, like Jamaica. Here we see another country here. So there are a few countries off the line. So this is not a perfect prediction. It's not even that good. It's only an approximation. And in the social sciences, I've heard 0.5 to be pretty good. You know, if you want sort of a ballpark figure mentally, or I have as an anchor point 0.5 to be there are some canonical works in sociology, for instance, where the regression is 0.5, so 50%. Before we had a much higher R-squared. In fact, I've seen people be criticized for having such a high R-squared because it doesn't make sense. And in fact, the more variables you put into, you know, when we talk about multiple regression models, like when we have multiple X's, if you put in too many predictors, you can have problems with your prediction model, and you can have an R-squared that's inappropriately high. That's just an artifact of the data. Oh yeah, okay. So now here we get to the components of the function, this arguments. I wanted to bracket this because I just wanted us to have fun with the analyses. But let's clean up our plot space. Now, okay, good. We didn't have that many plots. Sometimes I've had trouble with cleaning up the plot pane. These are also called panes, P-A-N-E. So the option here, you can define you can basically make a plot of the regression line, R as a regression line, or you can do just the points here. I think it's typically better to include both, right? We kind of want to see both. Okay, but that's just that component of the argument that I kind of wanted to bracket a little bit because it has this little C, this combine function here. Combine is a kind of a common little bit of R script. It's not a big deal. It just basically it says we want to put this P here and this R together. We're just combining the points and the regression line. The best statistics, I think, include data as well as the model. And the model is outlined. Okay, but the model also will consist of, if you read an academic paper, you'll see you know, predictors within a table. So let's take a look at this. We just printed in this model. Oh, whoops, I want to make sure we have the same model. So let's plot, whoops, sorry. I want to make sure we're also, sorry. I just printed the model, but I also wanted to plot that model with the predictor. So let's go to see how developed the country is. This is an index of economic, social development. Mostly, there's a whole theory of developmental economics, but we're looking at the level of developments. Typically, if you look at development here, we're often looking at, say, a poorer country like Guatemala is considered or defined as less developed than another country. So it looks like this is, in fact, this is just a factor variable. It looks like. Let's make sure this is a factor variable. Who cares? What I'm more interested in is actually showing you, and let's remove this. Let's keep our spaces clear. I'm going to remove this pane as well. I want us to think about the model as both a graphic and numbers. You know, we often emphasize numbers, but yeah, that's a pretty crummy model because it only has two values. But look at this. What is this? Well, I mentioned this earlier. What is the intercept? Well, it's y when x equals 0. What is, in a simple linear model, what is the coefficient? Well, it's the slope. If you know early, basic algebra, y equals mx equals mx plus b is sort of like what you might have learned in school, right? So to translate this, we don't typically use this notation in statistics, but just think about that simple linear model. The coefficient is this thing, so this is developed, and then you have the intercept is this value right here, and that's all that the prediction is. The prediction is simply you're plugging and chugging okay, what is the value of, you know, what is the value of y given the value of x? Well, we can do that pretty easy with this y equals mx plus b equation. Oops. I want to actually get rid of this. So, and you can, I think it's pretty intuitive. I think it's pretty easy to see that. We can see here's yeah. What else do I want to say? Oh, and negative slope, of course, is a negative association. Let's get a better variable. I'd like to see it. I think typically it's easier to visualize continuous variables, numeric variables. So let's look at, let's look at health. Why not? Are there any variables you guys want to see? If you can chat. All right, that's fine. Okay.
I did have a question though about predict.
Let's look at CO2. And I think one interesting thing about this is that when we think about murder rate and we think about predictors, sometimes these predictors might not make any sense. There's a famous, there's a mantra, correlation is not causation. And that is, of course, quite often the case with what is called observational data. If you recall, we first spoke about observational data. Observational data is not causal. These are not causal. But let's predict, okay, GDP. So that's basically the wealth of the gross domestic product of the country. Actually, health is sort of redundant. I think it's sort of tautological in the sense that you're defining health as a measure of health. Let's look at two continuous variables. Let's look at land area. Land area. I think I spelled that right. And we're going to see that association. Well, look at that. We have a huge outlier there, right? So this is an interesting fact about these data. This is an example of how outliers, you might want to remove this outlier here. But let's just pretend like this. We're gonna stick with this because actually it's quite common in statistics for people not to really look at the data. We're going to actually model murder rate as a function of land area. We're going to print that. We're going to see what that looks like. And it's in scientific notation, so it's a little difficult to interpret. So that's another issue here when we think about the units of the x's and the y. If these are very, very small, it's going to be difficult to interpret what the predicted values are. But let's just force our way through a bad model. Sorry, I'll take you on this odyssey. We're going to print this model. I already did this, and then we'll predict it. Predict model. Okay, so this is where predicted values help us, right? We couldn't really see the model, and this is why I think visualization is so wonderful, especially in the R environment, because we often you'll see often, and especially in science articles, you'll see the coefficients, but you won't see the predicted values. You won't see what it is actually estimated, right? These are estimates. These are the y-hats for every particular country. That's useful, I think, because it also tells us how off we can be at times, and how our predictions can vary if we drop or add a case. Let's see. Was there anything else I want to tell? Oh yeah, let's look at the R-squared. Do you think the R-squared will be high or low here of this model?
Low.
Is there anyone who's willing to tell me?
Low.
Anyone?
Low.
It's pretty low, right? What is that? 9%. As I told you before, that's not uncommon. But if this is where academics can debate, scientists can debate. You probably want to remove that outlier there. So.
Hey Nate,
the mean function. I think this is interesting to look at as well. So Did I do land? I did do land area. Right. So here we can look at the mean of the murder rate within each category. So I think that's another way of representing the data. So this is what I like about R, because what can you do with these objects now? Well, if you have the mean within each category of then you can actually define these as objects, or you can define the R² as objects, or you can say, okay, so this is murder rate and then land area, and you define that as an object. You should be able to do that. Let's see if we can. Yeah, okay, of course. And then you can print that, and I told you, right, you can just do that and ad infinitum. You can round that to, gosh, let's get those decimal places off. I don't really care. So there are a lot of different ways to play around with the data that I think are really useful. Someone did express a concern, and I couldn't run the mean function before. I wanted to see where that was again. Well, I'm not sure. Here we are. No, I'm not sure where that is. Okay. In any case, let's see if we can. Does anyone else have any other questions about this? I think it's important to. I want to focus on the homework at least.
Hey, Nate.
Okay. What is the proportion of variance that's not explained by our model? How can we calculate that? That's I think something that's interesting. So let's go to a better model. I don't like this murder rate one with land area. Let's go to let's look at GDP. I think GDP and murder rates, and we're going to predict this. But let's actually also create a plot out of that thing too. So I know I'm messing up all of the syntax, but we're going to do murder rate and GDP. I know it's the funny thing is it's when you do a lot of statistics, you can kind of forget about the fact that these are pretty serious issues that you deal with. On the other hand, I think this is the key importance of statistics. You're actually communicating and condensing information to show, to do really important work. I mean, this is not trivial to actually look at murder rates, global murder rates. I want us to start out with just the linear model, and so we define model with that, and then we're going to graph that model. Oh, look at this, GDP. Well, what does that mean? Well, I'm going to print our coefficients first. Here we have that. What this says is we have an intercept that's around 37. So when GDP is 0, we're getting a value of 37 for the murder rate. And it's basically nil near the end. The high GDP, the murder rate is basically nil. So this is actually quite informative. It really shows the inequality within our sample. It's pretty bifurcated. We can even predict those values for each country. So we can see that basically those countries with very low murder rates, the United States is actually one of them. Ukraine is quite high up there. Same as South Africa. So, but one of the questions we'll have is what is the proportion of what is the proportion of variation that is explained by the regression model? What is not explained by the regression model? The important thing I'm going to show you a little bit of math here. This is technically called the coefficient of alienation. No one really knows this. It's like a weird term, but this is 1 minus R². So how do we do this? Well, let's go back to the logic of object-oriented thinking. So first we're going to use that R² of our model. I want to make sure we're looking at GDP. So yeah, okay, good. Yeah, I know I'm not doing a good job cleaning up my workspace. I actually kind of I actually don't like to work in an environment where I'm not constantly cleaning up after myself. But I just want to show this to you. We're going to define as this is R². We're going to assign it to this value of model. So let's make sure we define model first, because remember, when you define an object, I keep defining the the object model using different predictors, right? Sometimes I'm using land area, sometimes I'm using other variables as predictors, X variables. So to be on the safe side, I would recommend, if you're using the same name for the same object, make sure you just rerun your little bit of script, reevaluate it, just to make sure that you're using the right prediction. And because we want to make sure that the R² that we now define is the correct one, and then we can print this. Sorry, print R². Sorry, there's a little bit of Boston in me. R². I didn't mean to say that. Okay. So what is 1 minus R²? Well, good. Let's just do the I don't know what to call this. Minus whatever. Inverse dot R². How about that? We assign as 1 minus that value. And then we should be able to print this. I'm just going to type it out because I'm tired of just typing out print. It's late in the day here. Okay, now if I did this right, we should have 1 minus this value. Yes, we do. Good. And of course, we can now take this. We can define this as rounding this. We can round our R². So then we take the object we just defined, and we're going to do round it, and we're going to do the inverse dot R. Oh, look, see, this is what I love about R too. Sometimes it'll give you these little things. I'm pointing as if you guys can see this. This is a base function. It is this kind of squiggly brackets and base. You know, when I was saying that if you close this pane up here, this graphics pane, you often can't see what's going on. That typically happens when you use the base graphics. We're in a much better, kind of happier world when we use these kinds of functions. But now let's round this sucker, and we're going to take it to 2. Did I do anything wrong there? No. See, this is why I like to have spaces. So we're going to define as a rounded one, and then we're going to print this. If you ever use Unix, this is kind of like using the echo function. If you do a for loop, I like to just see what I'm doing every once in a while. I actually don't even often look at the environment. I just want to be in the console. So this is nice, right? Here we have an answer. So one question would be, what is the proportion of variance that is not explained by our linear model? Well, it is this right here. It is 49, the coefficient of alienation. Don't ever say that, by the way. It's just, I think, a nice mnemonic. It's a kind of a funny phrase. I think it's simply an antediluvian turn of phrase. It simply means that which is not explained by our model. And of course, if you only have one predictor, would we really expect that to be our outcome to be predicted that much? Well, in this case, GDP seems to predict quite a bit. And this is I think speaks to this issue of model selection. What do you include as your predictors here? And we'll talk about that when we engage with multiple regression. So I want to make sure that we know when we talk about equations. Are there any questions about when we print the model itself, how to write that out as an equation?
Nate, you hear me?
That is GDP. I see. This is one thing to keep in mind whenever you print coefficients. These units often matter quite a bit. So often with income, for example, in the United States, we'll log the income, or we'll often standardize variables. Remember last week we talked about z-scores. Often it eases interpretation of these kinds of models. Let's see. We also have predicted values. We talked about that. Are there any other questions? Anything else? that you're curious about?
I had a question, Nate. Do you hear me?
Any questions you have? I think we're about up. Yeah, I could go on. I love linear regression models.
Hey, Nate, do you hear me?
If there are no questions, then thank you very much. Remember, my office hours are 1 to 3, and stay tuned for some tutorials. And if you have any requests for tutorials, email me. Okay, I'm going to actually request that. Email me at stat100nate@gmail.com. I think I have that email, right? Unless I'm just losing my mind. That is my correct email. Just feel free to contact me with any questions that you might have, because I'm here to help, and I think this is one of the most exciting sessions that we have, and it'll only get more exciting as we go from here. So, okay. Thank you very much, everyone. And any of you that might have other questions, you want to talk to me on one-on-one, you want to linger, I'm just going to stop the recording and the rest of you, if you want to, ask questions.